Let me tell you about the most boring particle in physics. I mean it. If you have ever looked at a diagram of an atom, any atom in any textbook, you have seen it sitting there, right in the middle, in the nucleus, next to the proton, doing absolutely nothing interesting. The proton gets to have a positive charge. That is a big deal. Charge means the proton interacts with electric fields, magnetic fields, and other charged particles. The proton is the thing that determines what element you are. 1 proton, hydrogen. 6 protons, carbon. 79 protons, gold. The proton is the star of the show. The electron is not exactly boring either. It has a negative charge. It orbits the nucleus. It forms bonds between atoms. It flows through copper wires and makes motors turn and light bulbs glow and your entire civilization run on electricity. The electron is the workhorse of chemistry. And then there is the neutron. Neutron, no charge. It just sits there, packed in the nucleus alongside the protons, like luggage in a trunk. Most people, when they learn about it, file it away as filler, nuclear ballast, the particle that adds weight but does not do anything exciting, the quiet roommate who pays rent but never once contributes to conversation. That is how we teach it. That is how most people think about it. And it is completely wrong. The neutron is not boring. The neutron is the most dangerous particle in the universe. It is the bullet that makes nuclear weapons possible. It is the projectile that nothing can stop because nothing can even see it coming. It is the particle that destroyed 2 cities in a single week in the summer of 1945. And there is more. That same particle, that same quiet, uncharged lump sitting in every nucleus of every atom of your body is also the reason you exist at all. Without the neutron, there would be no carbon, no oxygen, no iron, no water, no planet Earth, no stars in the sky, nothing but a thin, cold, boring haze of hydrogen stretching to the edge of the cosmos. The neutron is both the creator and the destroyer. And the fact that one particle manages to be both tells you something very deep about how nature works. So let me show you. Let me start by telling you how we found this thing in the first place. Because that story alone should make you suspicious that the neutron is anything but boring. For a long time, decades in fact, physicists thought they understood the inside of the atom. You had a nucleus in the center, small and heavy, carrying a positive charge. And you had electrons whizzing around outside, light and negative, balancing the charge. Protons and electrons. 2 characters, 2 charges, 1 atom. Simple. But there was a problem. A frustrating, persistent problem that would not go away no matter how much people tried to ignore it. The numbers did not add up. Take helium. Helium has an atomic number of 2, meaning 2 protons in its nucleus. Each proton has a mass of about 1 atomic mass unit, so you would expect helium to have an atomic mass of 2. But it does not. It has an atomic mass of 4. There is twice as much mass in the helium nucleus as the protons can account for. Where is the rest coming from? And it was not just helium. Carbon has 6 protons, but an atomic mass of 12. Nitrogen has 7 protons, but a mass of 14. Iron has 26 protons and a mass of 56. Every single element in the periodic table had this gap. The nucleus was always heavier than its protons alone could explain. The popular idea in the 1920s was that maybe there were extra protons hiding in the nucleus, with electrons stuffed in alongside them to cancel out the extra charge. So helium might have 4 protons and 2 electrons crammed inside the nucleus, giving atomic mass 4 and net charge 2. Sounds reasonable, right? Except when you work it out with actual physics, it falls apart. The Heisenberg uncertainty principle tells you that if you confine an electron to a space as small as an atomic nucleus roughly a femtometer across, the uncertainty in its momentum becomes enormous. You can calculate it. The momentum would be so large that the electron's kinetic energy would be in the hundreds of millions of electron volts. That is far more energy than the nucleus could contain. The electron would burst right out. And even apart from that, the spin properties of nuclei, their magnetic moments, their angular momenta, none of it matched the predictions of the proton-electron model. Nature was screaming that the theory was wrong. There was something else in there, something nobody had detected. Ernest Rutherford, who had discovered the nucleus back in 1911, by shooting alpha particles at gold foil, knew something was missing. In a lecture in 1920, He speculated that there might be a neutral particle, something with about the same mass as a proton but no electric charge, lurking inside the nucleus. He even gave it a name. He called it the neutron. But it was just speculation. How would you even detect such a thing? All your instruments rely on electric charge to spot particles. Charged particles leave tracks in cloud chambers. They ionize gas in Geiger counters. They curve in magnetic fields. A neutral particle would do none of those things. It would be a ghost. For 12 years, Chadwick, Rutherford's protege at the Cavendish Laboratory in Cambridge, kept that idea alive. He ran experiments, he searched, he came up empty. 12 years is a long time to chase a ghost. Then in late 1931, a report arrived from Paris that changed everything. Irene Joliot-Curie and Frederick Joliot, the daughter and son-in-law of Marie Curie, were studying what happens when you bombard beryllium with alpha particles from a polonium source. They observed a mysterious radiation emerging from the beryllium. It was intensely penetrating. It sailed through centimeters of lead, through walls, through materials that would stop any known radiation. The Joliot-Curies concluded it must be very energetic gamma rays, the highest energy photons anyone had ever seen. And then they noticed something strange. When this radiation hit paraffin wax, which is rich in hydrogen atoms, it knocked protons out of the wax at high speed. This was the detail that caught Chadwick's attention. Because think about the physics. A photon has no mass. A proton is massive. Trying to knock a proton loose with a photon is like throwing a table tennis ball at a cannonball and expecting the cannonball to fly across the room. Conservation of energy and momentum say you would need a fantastically energetic photon to do that, far more energetic than anything known. The energy accounting did not work. Chadwick took the Joliot-Curie results to Rutherford. The old man's reaction, according to the legend, was immediate and definitive. I do not believe it. Neither did Chadwick. He dropped everything and started his own experiments. What followed was one of the most concentrated bursts of discovery in the history of science. Working almost around the clock for roughly 2 weeks, Chadwick bombarded beryllium with alpha particles and studied the outgoing radiation by aiming it at various targets: paraffin wax, helium gas, nitrogen, lithium. He measured the recoil energies of the particles knocked out of each target, and the results were consistent, beautifully consistent, with one explanation and one explanation only. The radiation was not photons, it was particles, neutral particles, with a mass almost exactly equal to the proton. He had found the neutron. In February of 1932, he published a cautious paper titled The Possible Existence of a Neutron. By May, he had the definitive result and published the existence of a neutron in the Proceedings of the Royal Society. 3 years later, he received the Nobel Prize, and the Joliot-Curies, who had the data but drew the wrong conclusion, missed that particular prize, though they would win their own Nobel in chemistry shortly afterward for discovering artificial radioactivity. Science is like that sometimes. The data is right in front of you, and the difference between a Nobel Prize and a footnote is whether you interpret it correctly. Chadwick's discovery was like finding a missing piece that suddenly makes the entire jigsaw puzzle click together. Werner Heisenberg over in Germany immediately proposed a new model of the nucleus. Forget protons and electrons crammed together. The nucleus is made of protons and neutrons. Period. The number of protons gives you the element. The number of neutrons can vary, and that gives you isotopes, different versions of the same element with different masses. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. Carbon-14 has 6 protons and 8 neutrons. Same element, same chemistry, different mass. The neutron explained isotopes instantly. It explained nuclear masses. It explained nuclear spins. It was the missing character in a play that suddenly made every scene make sense. And something else became clear almost immediately. Because the neutron has no electric charge, it is not pushed away by the positive charge of a nucleus. A proton trying to approach another nucleus faces a tremendous electromagnetic barrier, like trying to push through a wall of invisible force. The closer it gets, the harder the wall pushes back. But a neutron does not see that wall at all. It walks right through. This made the neutron the perfect probe, the perfect projectile for studying nuclear structure, and as people would soon realize, the perfect trigger for splitting atoms apart. Enrico Fermi, in Rome, seized on this almost immediately. Starting in 1934, just 2 years after the neutron was found, Fermi and his group systematically bombarded every element they could get their hands on with neutrons. They went down the periodic table, element by element, to see what would happen. And they made an unexpected discovery. Slow neutrons, neutrons that had lost energy by bouncing through paraffin or water, were far more effective at being captured by nuclei than fast ones. This was counterintuitive. You might think a faster bullet would be more penetrating. But a slower neutron spends more time in the vicinity of the nucleus, and the probability of capture increases dramatically. It is like the difference between hurling a ball past a basket at 90 miles an hour and lobbing it gently. The gentle lob has a much better chance of going in. Fermi won the Nobel Prize in 1938 for this work, and his slow neutron technique became the cornerstone of everything that followed, from nuclear reactors to weapons. But I am getting ahead of the story. Before I show you what happens when you fire neutrons at heavy nuclei, let me explain why the neutron matters, for the most basic thing of all. Why atoms can exist. Why the periodic table does not end at hydrogen. Imagine you are building a nucleus. You start with one proton. That is hydrogen. Fine, now you want to add a second proton to make helium. But there is a problem. Both protons have a positive charge, and positive charges repel. The electromagnetic force between them is trying to push them apart. At the distance of 1 femtometer, which is about how close nucleons sit inside a nucleus, the repulsive force between two protons is on the order of 230 newtons. For particles that small, that is a staggering force. It is as if each proton was shoving the other away with the strength of a small engine. So what keeps them together? A different force. The strong nuclear force. This is a force that acts between all nucleons, protons, and neutrons alike, and at very short range it is enormously powerful, about 100 times stronger than the electromagnetic repulsion. But it has a catch. The strong force has a very limited reach. Beyond about 1 to 2 femtometers, it drops to essentially zero. It can only hold on to its nearest neighbors. The electromagnetic force, on the other hand, has infinite range. A proton on one side of a large nucleus still feels the repulsion of a proton on the opposite side, even though the strong force between them has faded to nothing. This means there is a competition, a tug of war. The strong force is pulling nucleons together. The electromagnetic force is pushing protons apart. For small nuclei, the strong force wins easily because every nucleon is close to every other nucleon. But as you add more protons, the electromagnetic repulsion piles up across the entire nucleus, while the strong force only acts locally. At some point, the repulsion threatens to overwhelm the attraction. Enter the neutron. The neutron contributes to the strong force just like a proton does. It pulls on its neighbors with the same strength, but it adds zero electromagnetic repulsion. None. Because it has no charge. Adding a neutron to a nucleus is like hiring a builder who works for free and does not argue with anyone. It is pure benefit. More binding, more stability, no additional cost. Let me give you an analogy that might help. Imagine you are building a dome out of bricks. The bricks are heavy, and they press together under gravity, which is good because that compression holds the dome up. But some of the bricks are also magnetic, and they repel each other. The more magnetic bricks you add, the more the dome wants to fly apart. The solution? Add non-magnetic bricks between the magnetic ones. They contribute to the weight and the structural compression, but they do not add any repulsion. That is what neutrons do in the nucleus. They are the non-magnetic bricks. They add binding without adding conflict, and the bigger the dome gets, the more non-magnetic bricks you need, because the magnetic repulsion reaches farther and farther across the structure, while the compressive holding force is purely local, brick by brick. That is why every element heavier than hydrogen needs neutrons. And the heavier the element, the more neutrons it needs. And think of it like building a taller and taller tower out of magnets. The more magnets you stack, the more they repel each other, and the more non-magnetic spaces you need to keep the tower from blowing itself apart. Helium gets by with a 1-to-1 ratio. 2 protons, 2 neutrons. Iron needs 30 neutrons for 26 protons. By the time you reach uranium, you have 92 protons but need 146 neutrons. Without those extra neutrons absorbing the electromagnetic strain, the nucleus would explode. Without neutrons, the periodic table ends at hydrogen. One element, one kind of atom, no molecules, no chemistry, no stars, because stars are built from hydrogen and helium and heavier elements. No planets, no oceans, no DNA, nothing. So the boring particle is actually the structural foundation of every complex atom in the universe. Surprise number one. Now let me show you what happens when this particle leaves home. Because the neutron's behavior inside the nucleus and outside the nucleus are so different, it is almost as if you are dealing with two different particles. Inside a stable nucleus, a neutron can last for billions of years. It is bound, comfortable, protected. The strong force keeps it locked in place. But if you extract a neutron, if you set it free, it dies. On average, in about 14 minutes and 39 seconds. That is its mean lifetime. The half-life is just over 10 minutes. Start with 1,000 free neutrons floating in empty space, and 10 minutes later, roughly 500 of them have vanished. Another 10 minutes, about 250. They are not just disappearing. A free neutron undergoes beta decay. It turns into a proton, an electron, and an electron antineutrino. At the deepest level, what happens is this. The neutron is made of 3 quarks, 2 down quarks and 1 up quark. During beta decay, one of the down quarks emits a W- boson, a carrier particle of the weak nuclear force, and in doing so changes its flavor from down to up. That converts the quark composition from 2 down 1 up to 1 down 2 up, which is a proton. The W- boson is incredibly short-lived. It decays almost instantly into the electron and the antineutrino that fly away carrying energy and momentum. The reason this happens is mass. The neutron is slightly heavier than the proton. The difference is tiny, only about 1.3 million electron volts. In percentage terms, the neutron is less than 0.1% heavier, but that fraction of extra mass provides just enough energy to produce the proton, the electron, and the antineutrino. The books balance. The decay is allowed, so it happens. Slowly, probabilistically, 1 neutron at a time, over the course of about 15 minutes. Inside the nucleus, this decay is blocked. The binding energy from the strong force changes the energy landscape. It effectively makes the neutron lighter than it would otherwise be, or equivalently, raises the energy cost of the proton plus electron plus antineutrino system, so that the decay becomes energetically forbidden. The strong force stabilizes the neutron by making the exit door too expensive to open. Free the neutron. Remove that binding energy, and the exit door swings wide open. 14 minutes and 39 seconds. This is the detail that makes the neutron so dangerous. Because a free neutron, being electrically neutral, can approach any atomic nucleus without being repelled. A proton, carrying positive charge, faces a towering electromagnetic barrier when trying to enter a positively charged nucleus. The closer it gets, the stronger the repulsion. It is like running uphill against a gale. But the neutron does not feel any of this. It walks straight in. No resistance, no barrier. It is the perfect nuclear projectile. And when it enters the right kind of nucleus, specifically uranium-235, the result is catastrophic. Uranium-235 has 92 protons and 143 neutrons. It is already strained. The electromagnetic repulsion among those 92 protons is barely being contained by the strong force and its 143 neutron helpers. Then one more neutron drifts in. The nucleus swallows it and becomes uranium-236. This new arrangement is violently unstable. The nucleus begins to deform, oscillating like a drop of water on a vibrating surface. It elongates, it pinches in the middle. Ask yourself this: what happens to a rubber band when you stretch it too far? At some point, the restoring force cannot keep up, and the band snaps. That is what happens next. In that stretched out shape, the strong force, which only works at short range, loses its grip across the length of the nucleus. The electromagnetic repulsion, which has been restrained by the thinnest of margins, seizes its chance. The nucleus tears apart. This is fission. The uranium splits into 2 large fragment nuclei, typically barium and krypton or similar pairs, releasing an enormous burst of energy, about 200 million electron volts per fission event. Compare that to a chemical reaction like burning gasoline, which releases a few electron volts per molecule. Fission is roughly 50 million times more energetic per event. But the critical detail, the one that changed the trajectory of human civilization, is not the energy, it is the neutrons. When a uranium-235 nucleus splits, it releases, on average, 2 to 3 additional free neutrons. Those neutrons are fast. They fly out into the surrounding material, and if they encounter another uranium-235 nucleus, they can trigger another fission, which releases 2 to 3 more neutrons, which trigger more fissions. 1 becomes 3, 3 becomes 9, 9 becomes 27. This is a chain reaction, and here is where you have a fork in the road, and the fork leads to 2 very different destinations. If you slow the neutrons down using what is called a moderator, something like water or graphite that the neutrons bounce off of and lose energy, you can control the cascade. You arrange the uranium in rods, surround them with the moderator, and insert control rods made of materials that absorb neutrons like cadmium or boron. Push the control rods in, and they soak up enough neutrons to slow the chain reaction. Pull them out, and the reaction speeds up. You can tune it so that, on average, exactly 1 neutron from each fission event goes on to cause another fission. A sustained, steady, controlled reaction. That is a nuclear reactor. It generates heat. The heat boils water. The steam turns turbines. The turbines generate electricity. About 10% of the world's electricity comes from this process, from neutrons hitting uranium nuclei one at a time in a carefully regulated dance. But if the fissile material is sufficiently enriched and packed into a dense enough mass, a so-called critical mass, then the chain reaction does not need moderating. It runs away. The neutron population doubles and doubles and doubles again in millionths of a second. The energy release is so fast and so concentrated that the result is an explosion, not a chemical explosion, a nuclear explosion, thousands of times more powerful than any chemical explosive humanity has ever produced. I want you to appreciate a peculiarity of this situation. The difference between a nuclear reactor that provides electricity to a city and a nuclear weapon that destroys a city is at its core a matter of neutron management. How many neutrons are absorbed? How many are slowed? How many are allowed to continue the chain? The neutron is the lever. Push it one way and you power a hospital. Push it the other way and you level one. On August 6, 1945, a uranium bomb was dropped on the Japanese city of Hiroshima. Roughly 80,000 people died immediately, many more in the weeks and months that followed. 3 days later, a plutonium bomb was dropped on Nagasaki. Both weapons were triggered by neutrons, by the quiet particle with no charge. Think about the timeline. Chadwick found the neutron in 1932. Just 6 years later, in 1938, Otto Hahn and Fritz Strassmann in Berlin discovered that bombarding uranium with neutrons caused fission. The news reached physicists around the world almost overnight. Within months, several groups independently realized that fission released extra neutrons, making a chain reaction possible. Enrico Fermi, an Italian physicist who had done some of the earliest experiments bombarding elements with neutrons, built the first controlled chain reaction in a squash court under the bleachers of the University of Chicago in December of 1942. 3 years after that, the bombs fell on Japan. From discovery to devastation, 13 years. That is how fast physics can move when the particle you have found is the right key for the most dangerous lock in nature. James Chadwick, who had found the neutron only 13 years before the bombings, understood what his discovery meant the moment chain reactions became plausible. He said he realized a nuclear bomb was not only possible but inevitable. He said the only remedy he found was sleeping pills. But the neutron is not merely a weapon. I told you it keeps you alive. And I know that sounds absurd. You have just heard me describe a particle that leveled a city. How can the same thing be the reason you are breathing right now? Let me slow down for a moment. Take a breath. Because the next part of the story requires us to think on a completely different scale. Not the scale of a bomb, or a laboratory, or even a planet. The scale of the entire universe. And the clock on this next story is not 13 years. It is 13.8 billion. About 13.8 billion years ago, the universe began in an unimaginably hot, dense state. In the first second, temperatures exceeded 10 billion degrees. Protons and neutrons were being created and destroyed constantly, converting back and forth through weak force interactions. A proton absorbs an electron and becomes a neutron. A neutron emits an electron and becomes a proton. At those temperatures, the interconversion was rapid, and the two species were in thermal equilibrium. But the universe was expanding, cooling, and the weak interactions that shuffled protons and neutrons back and forth gradually fell behind the expansion rate. About 1 second after the Big Bang, at a temperature of roughly 10 billion degrees, the conversion froze out, At that moment, the neutron-to-proton ratio locked in at about 1:6. Slightly more protons than neutrons because the neutron is a bit heavier and the thermal equilibrium favored the lighter particle. Why 1:6 and not 1:1? Because of that tiny mass difference again. The neutron is about 1.3 million electron volts heavier than the proton. In thermal equilibrium, the heavier particle is always slightly less abundant. The ratio between them depends on the temperature and the mass difference following a distribution from statistical mechanics. At 10 billion degrees, the math works out to roughly 1 neutron for every 6 protons. If the mass difference were 0, the ratio would be 1:1, and you would get a very different universe. If it were larger, you would get even fewer neutrons. That 1.3 million electron volts keeps showing up, does it not? One number echoing through everything. And then the countdown began. Every free neutron had about 15 minutes before it decayed into a proton. If nothing grabbed those neutrons, locked them into nuclei, they would all disappear, and you would be left with a universe of pure hydrogen. Nothing else. Just protons and electrons floating in expanding space forever. No helium, no lithium, no stepping stones to heavier elements, no raw material for stars to build carbon and oxygen from. The universe would be chemically dead on arrival. But nature had a narrow window, and I want you to picture this because it is one of the most dramatic moments in cosmic history and nobody was there to see it. Imagine the entire observable universe, everything you can see in every direction, compressed into a volume smaller than our solar system is today. Blindingly hot, opaque with radiation, a soup of particles colliding billions of times per second. In that environment, protons and neutrons are slamming into each other constantly, and the first thing that can stick is deuterium, 1 proton bound to 1 neutron, the simplest composite nucleus. But deuterium has a low binding energy. It is fragile, and the universe at this stage is still flooded with high-energy photons. Every time a deuterium nucleus forms, a photon smashes it apart. It is like trying to build a sandcastle while someone keeps kicking it over. This is called the deuterium bottleneck, and it is one of the most important choke points in all of cosmology. Until the photons cool down enough to stop breaking deuterium, nothing heavier can form, and meanwhile the neutron clock keeps ticking. Every second, more neutrons are decaying into protons and slipping away. Around 3 minutes after the Big Bang, the bottleneck finally breaks. Deuterium survived, and once deuterium survived, the subsequent reactions happened fast. Deuterium plus a proton made helium-3. Deuterium plus a neutron made tritium. 2 deuterium nuclei could fuse directly to make helium-3 plus a leftover neutron, or tritium plus a leftover proton, and the helium-3 and tritium quickly combined to form helium-4, which is extraordinarily stable. 2 protons, 2 neutrons bound together with a very high binding energy. Almost every surviving neutron ended up locked inside helium-4. This whole process, Big Bang nucleosynthesis, took about 17 minutes from start to finish, a cosmic sprint. By the time 20 minutes had passed after the Big Bang, the universe had cooled and thinned too much for further nuclear reactions. The window slammed shut, and the cosmic inventory was set. The result: for every 7 protons in the universe, about 1 neutron survived and got locked into helium. By mass, the universe was roughly 75% hydrogen and 25% helium, with tiny traces of deuterium and lithium-7. That inventory, set by the neutron's lifetime and the expansion rate of the universe, became the raw material from which everything else would eventually be made. If the neutron lived much longer, say a few hours, far more neutrons would survive to be captured, and the universe would be dominated by helium. Think about what that means for stars. Stars are essentially giant balls of nuclear fuel burning through fusion. Our sun fuses hydrogen into helium, and it has been doing this for about 4.5 billion years. That slow burn is what gave Earth enough time for oceans to form, for chemistry to get interesting, for single-celled life to appear, for evolution to do its patient work. A helium-dominated universe would produce stars that burn differently, faster, less patiently. The window for life narrows dramatically. If the neutron lived much shorter, say only a minute, nearly all neutrons would decay before nucleosynthesis even began. The result would be a universe of almost pure hydrogen, with only the faintest trace of helium, and without primordial helium as a stepping stone, the chain of nuclear reactions inside stars that builds carbon, oxygen, nitrogen, and all the elements of life gets stuck. The triple alpha process, which fuses 3 helium nuclei into carbon, requires helium to exist in the first place. No helium, no carbon. No carbon, no organic chemistry. No organic chemistry, no life of any kind we can imagine. There is a deeper point here that I do not want you to miss. The neutron's lifetime is not something that was chosen or tuned. It falls out of the physics, out of the masses of the quarks and the strength of the weak force. Nobody adjusted a dial. But if that number had come out significantly different in either direction, the universe would be a chemically impoverished place, incapable of producing the complexity we see around us. That is either a coincidence or a clue. I honestly do not know which, but it is worth sitting with. The neutron's 15-minute lifetime sits in a sweet spot, long enough for a healthy fraction to survive until fusion grabs them, short enough that the universe ends up with plenty of hydrogen left over. That balance, struck in the first 20 minutes of cosmic history, echoes through every star and planet and living thing that exists today. And the neutron's work did not stop there. Not even close. Inside stars, nuclear fusion chains build elements up to iron, which has 26 protons. Hydrogen fuses to helium. Helium fuses to carbon through the triple alpha process. Carbon fuses to oxygen. Oxygen to neon and magnesium, then to silicon, and silicon to iron. Each step releases energy and sustains the star. But iron sits at the top of the binding energy curve. Fusing iron does not release energy, it absorbs it. Iron is the dead end of stellar fusion. So how does nature build anything heavier than iron? How do you get to copper, zinc, silver, tin, gold, platinum, lead, thorium, uranium? The answer is neutron capture. In certain stellar environments, free neutrons bombard existing nuclei. A nucleus absorbs a neutron and becomes a heavier isotope of the same element. Absorb another, get heavier still. Eventually, a neutron inside this bloated nucleus may beta decay into a proton, bumping the atomic number up by 1 and creating the next element on the periodic table. Then the process continues. The slow version of this, called the S process, happens in the outer layers of red giant stars over hundreds to thousands of years. These are old, bloated stars near the end of their lives. Inside them, nuclear reactions produce free neutrons as byproducts. Those neutrons drift outward and get absorbed by nuclei in the surrounding stellar material. One neutron at a time, the nucleus grows heavier. Eventually, a neutron beta decays to a proton. The atom moves up one spot on the periodic table, and the process repeats. It is like filling a bucket, one drop at a time. Slow, steady, patient. This process builds elements from iron, all the way up to bismuth, which has 83 protons. But to go beyond bismuth, to make the truly heavy elements, you need something far more violent. The rapid version, the raw process, is nuclear alchemy at its most extreme. It occurs in environments where the neutron flux is not a trickle but a flood, a deluge, inside the collapsing core of a supernova or in the debris thrown off when two neutron stars spiral together and collide. In those environments, nuclei absorb not 1 or 2 neutrons but dozens in fractions of a second, far faster than beta decay can act. The nuclei swell with excess neutrons, pushed far from the valley of stability into exotic, short-lived territory that does not exist under normal conditions. When the bombardment finally ends, these bloated nuclei undergo a cascade of beta decays, shedding their excess neutrons as protons, and in the process landing on the heaviest stable elements of the periodic table: gold, platinum, uranium, thorium. Think about that. 2 neutron stars, each about 10 miles across, each packing more mass than our sun into a ball the size of a city, spiraling closer and closer over millions of years until they slam together at a significant fraction of the speed of light. The collision sends shock waves through space-time itself, gravitational waves rippling outward at the speed of light. The impact generates temperatures in the billions of degrees, and for a brief period the merged object is the most energetic thing in the local universe. It ejects a plume of neutron-rich debris into space, a spray of matter so dense and so rich in neutrons that there is nothing else like it anywhere in nature. And that debris, in the fraction of a second while it is still blisteringly hot and dense, undergoes the R process. Neutrons flood into nuclei. Beta decays cascade. And when the debris expands and cools, drifting out into the darkness, it contains atoms of gold, platinum, iodine, and dozens of other heavy elements that simply cannot be made any other way. In 2017, astronomers detected a neutron-star merger for the first time by its gravitational waves, and then watched the afterglow with telescopes. The light from that afterglow had the spectral signatures of heavy elements. We were watching gold being made in real time across the universe. 130 million light-years away, two neutron stars smashed together, and the debris cloud was laced with freshly forged heavy elements, enough gold to outweigh our sun several times over, all manufactured by the neutron under the most extreme conditions nature can produce. Those atoms mix into gas clouds. The gas clouds collapse to form new stars and planets. The heavy elements concentrate in the rocky inner planets. Billions of years later, someone digs them out of the ground and puts them on a ring. Every atom of gold you have ever touched was built this way, by neutrons, in one of the most violent events the universe can produce. And I should say one more thing about neutron stars themselves, because they are among the strangest objects in existence. When a massive star exhausts its fuel and its core collapses, the protons and electrons in the core are squeezed together so violently that they merge. Protons absorb electrons and become neutrons. The entire core converts into a ball of neutrons packed so tightly that a teaspoon of the material would weigh about 1 billion tons. A neutron star is essentially a giant atomic nucleus 10 miles across, containing more mass than our sun, and these neutrons, despite being free of any normal nucleus, do not decay. Because the gravitational binding energy is so enormous, the energy landscape is completely different from a free neutron floating in space. The strong force combined with gravity at this extreme holds them stable. So the neutron, which cannot survive for even 15 minutes in empty space, can form an entire star that lasts for billions of years, provided you pack enough of them together. Nature is funny that way. So let me tally the score. Without neutrons, no nuclei beyond hydrogen can exist. Without the neutron's specific 15-minute lifetime, the Big Bang produces the wrong mix of hydrogen and helium, and stellar chemistry fails. Without neutron capture in stars and stellar explosions, no element heavier than iron is possible. The same boring, uncharged particle is responsible for atoms, for the primordial recipe, and for the entire heavy end of the periodic table. And when liberated from its nuclear home, that same particle can trigger the most destructive weapon ever built. One more thing. A puzzle genuinely unresolved. When physicists measure the neutron's lifetime with extreme precision, they get two different answers depending on how they measure it, and the discrepancy has not gone away. Method 1 is the bottle. You trap ultra-cold neutrons moving only a few meters per second, in a magnetic or material container. These ultra-cold neutrons are remarkable. Normal neutrons from a reactor move at millions of meters per second, but if you cool them down enough, they slow to a walking pace, and at that speed they will reflect off certain materials like beryllium or be held in place by magnetic field gradients. You can literally trap them in a jar, count how many you start with, wait a known amount of time, count how many survive. From the rate of disappearance, you calculate the lifetime. Bottle experiments, particularly the most precise one done at Los Alamos with a magnetic trap the size of a bathtub, give a mean lifetime of about 878 seconds. The precision on that number is extraordinary, down to fractions of a second. Method 2 is the beam. Send a well-characterized stream of cold neutrons through a magnetic trap that captures the protons produced by beta decay. You know, the neutron flux going in, you count the protons coming out, and from that ratio you calculate the lifetime. Beam experiments, particularly the definitive one at the National Institute of Standards and Technology, give about 888 seconds. The difference is about 9 seconds. For a long time, everyone assumed this was just the difficulty of the measurements. Both methods are extraordinarily hard, each plagued by different systematic errors. But as the experiments have improved over decades, as error bars have shrunk, the gap has stubbornly persisted. The statistical significance is now close to 4 standard deviations. In physics, that is a serious discrepancy. The intriguing possibility is this. The bottle counts total neutron disappearances from all causes. The beam counts only the protons produced by standard beta decay. If both are right, the difference means some neutrons are vanishing without producing protons. They are going somewhere else, a hidden decay channel. Into what, in 2018, a pair of physicists proposed that the neutron might occasionally decay into a dark matter particle. If roughly 1% of decays went to some dark sector particle instead of the standard proton-electron-antineutrino trio, it would explain the 9-second gap. This was exciting because it would be the first direct link between ordinary matter and the dark matter that makes up about 85% of the universe's mass. Experiments followed. Physicists looked for photons and electron-positron pairs that certain dark decay models predicted. Nothing. A team at Oak Ridge National Laboratory searched for mirror neutrons, a hypothetical dark twin that the neutron might oscillate into and back. The idea was almost science fiction. If a mirror world exists, a shadow version of our particle zoo with its own forces and interactions, then a neutron might occasionally quantum mechanically oscillate into its mirror counterpart, becoming invisible to all our detectors. It would appear to vanish without decaying at all. To test this, they built an experiment at the spallation neutron source. They fired a beam of neutrons at a wall made of boron carbide, a powerful neutron absorber. Ordinary neutrons would be stopped dead, but if a neutron oscillated into a mirror neutron, it would pass through the wall like a ghost, because mirror matter does not interact with ordinary matter except through gravity. On the other side of the wall, they placed detectors waiting to see if any mirror neutrons oscillated back into normal neutrons and showed up. Nothing came through. The mirror neutron hypothesis, in its simplest form, was ruled out. So the puzzle stands, 9 seconds unaccounted for. We do not know if it is a hidden systematic error, or a door to physics beyond the standard model. The neutron is keeping a secret, and we have not cracked it yet. I find that beautiful. After 90 years, after building reactors and weapons and mapping the entire periodic table with its help, we have not completely figured out this one particle. Let me close with the question of mass, because that tiny mass difference I mentioned, the one that makes the neutron just barely heavier than the proton, is one of the most consequential numbers in all of physics, and the consequences go even further than what I have shown you. If the neutron were lighter than the proton instead of heavier, the proton would be unstable. Protons would beta decay into neutrons. Hydrogen, which is just a proton with an electron, could not exist as a stable atom. No hydrogen means no water, no hydrogen-fueled stars, no hydrogen bonds holding proteins and DNA together. Chemistry collapses. Life is impossible. If the neutron was significantly heavier, say by a few more million electron volts, it would decay so fast that none would survive the Big Bang. The universe would be pure hydrogen, no helium, no stepping stone for stellar nucleosynthesis, no pathway to carbon, oxygen, or anything else needed for planets and biology. The mass sits in a razor-thin window, just barely heavier than the proton, enough to make the neutron unstable when free, but not so much that it decays too quickly to be useful. We do not know why the quark masses, which determine the neutron mass through quantum chromodynamics, have the values they do. We can calculate the neutron mass approximately from first principles, and the theory of quantum chromodynamics gives numbers that match experiment quite well. Lattice QCD calculations, where you simulate the strong force on a computer by discretizing spacetime into a grid and computing how quarks and gluons interact, have gotten good enough to reproduce the neutron-proton mass difference. That is a triumph of the theory. But the inputs to the calculation, the quark masses and the coupling constants, are measured quantities. We plug them in. We do not derive them from anything deeper. We do not know why the down quark is slightly heavier than the up quark, which is ultimately what makes the neutron heavier than the proton. That is just what they are. Whether this is evidence of fine-tuning, or a selection effect, or a clue pointing to some deeper theory, I cannot tell you. What I can tell you is that a mass difference of less than 1 part in 1,000 between two particles that are otherwise nearly identical makes the difference between a universe full of stars and chemistry and life and a universe that is a cold, thin soup of hydrogen going nowhere. Now look at yourself. Right where you are, sitting or standing, there are neutrons inside you. Trillions upon trillions of them. Every carbon atom in your muscles has 6 neutrons. Every oxygen atom in the water running through your veins has 8. Every calcium atom in your bones has 20. Every iron atom in the hemoglobin carrying oxygen in your blood has 30. They are all sitting there, locked in by the strong force, perfectly stable, doing their job, quietly holding your atoms together. Some of those neutrons were forged in the first 20 minutes of the universe, when everything was a plasma fireball and the laws of physics were deciding, through nothing more than the interplay of forces and decay rates and expansion speeds, what the cosmos would be made of. Others were built inside massive stars that lived and died before our solar system was even a cloud of gas fused in stellar cores and flung into space by supernovae. And a few of the heaviest ones, sitting in trace elements like iodine and molybdenum that your body needs in tiny amounts, were almost certainly made in the collision of neutron stars, in an event so violent it briefly outshone an entire galaxy and sent gravitational waves rippling through the cosmos. All of those neutrons are in you right now, holding you together. The neutron, the most boring particle in physics, the most dangerous particle in physics, and the particle that keeps you alive. If you had to pick one particle, just one, that best captures the strange, terrifying, beautiful duality of how the universe works, the fact that the same thing can create and destroy, can sit quietly for billions of years, or dissolve in 15 minutes, can hold your bones together, and also trigger the most powerful weapon humanity has ever built, which particle would it be? I know my answer. I would love to hear yours.